Okay, in this video we're going to have a look at conditional probability for multi-stage problems. So more than one stage in the problem, and just like normal multi-stage problems, it's tree diagrams is a good way to go for these sort of questions. These are probably the more trickier kind of conditional probability questions. So we'll have a look at this through two examples. We'll try and cover the theory. Bag contains 2 red, 1 black, 1 white. Andrew selects 1 ball from the bag, keeps it hidden. Okay, then he selects a second ball, also keeping it hidden. So that makes it very clear, no replacement. We're not replacing. He's taken a ball, keeping it hidden, then taking a second ball. Draw a tree diagram to show all possible outcomes. Okay, you could do it with two R's like this, but I think it'll be a bit easier if we use probabilities, less branches. So I'm going to do a probability tree diagram. Okay, so try and draw it reasonably big, probably bigger than what I've just done. Red, black, white. There are 2 out of 4 are red, 1 out of 4 is black, and 1 out of 4 is white. And then we're not replacing. So if I've selected a red, I've got 1 less red, so I'll have a 1 out of 3 chance now. If I've taken away 1 red, I've got three balls left. 1 is red, 1 is black, 1 is white. So red, black, white, red, black, white, and each of these has a 3rd chance. Okay, if the first ball that I took was a black ball, that black ball's gone. I've now got 2 reds and 1 white left to play with. So 2 red and 1 white. So 2 out of 3 are red, 1 out of 3 is white. Or if I selected the white ball to begin with, I now have no more white balls. I've got 2 red balls and 2 black. So red and black. So 2 out of 3 would be red and 1 out of 3 would be black. Okay, I'll just write down outcomes at the end. So we've got red, 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 black, red, white, white, sorry, black, red, black, white, white, red, and white, black. That's part A done. Part B. Find the probability that both selected balls are red. So part B, we want to work out probability of red, red. Okay, so multiplying across the tree diagram, 2 out of 4 times 1 out of 3. Simplifying, that's going to be 1 out of 6. C. Find the probability that at least one of the selected balls is red. Find the probability that at least one of the selected balls is red. So we want at least 1 red. P bracket at least 1 red. Now you can go through and tick all the ones that have at least 1 red, so 1 red or more. But I think what you'll find is that there's many cases it's probably easier to do look at the complement. The complement of at least 1 red would be no red. So the 2 options for no red are black white and white black. So that's much easier to calculate, a lot less working out is required. So black white going across the tree diagram, multiplying 1/4 times 1/3, and white black going across the tree diagram, multiplying it's 1/4 times 1/3. Okay, so when you do that, you get 2 twelfths, so 1 out of 6. 1 minus 1 out of 6, which is 5 out of 6. Okay. Before we move on, I just want to quickly show you how conditional probabilities kind of work in tree diagrams. So this first stage, it's probably getting red first, black first, white first. But these here, the second column, they're different probabilities dependent on what you've selected first. So you could write down this, for example, this one here, you could write this as probability of getting black on the second, given that we got a white on the first. Okay, so this 1/3 here means the probability of getting black second, given that white was first. So each of these second stage can be written as a conditional probability. So just be aware of that. that can be quite helpful for these multi-stage events. Anyway, on to this question. This question's an interesting one, D. I like this question. So Andrew drops one of the selected balls. We can see it is red. So he drops one and one is red. What's the probability that the ball still hit and is also red? The first thing is we don't know which ball he dropped. Did he drop the first ball or the second ball? We don't know. But all we know is that he's dropped a ball and it is red. So therefore, it is definite that there is at least one red. And we want to know what's the probability that the second ball, the one he's still got in his hand, is red. So what this question's asking for is to work out the probability of getting red given at least one was red. We know at least one is red because he's dropped it and we can see it's red. We want to know the probability that both are red. Okay, so by definition of conditional probability, that'll be the probability of red, and at least one red over the probability of the back bit, which is at least one red. Okay, we know the answer for the denominator. We've worked it out. 5 out of 6. We need to think about the top. So let's consider each one separately. So red would be the top there. And at least one red is all the ones that I've ticked from before. Now, can you see that we're after the intersection of red and at least one red? So the intersection means it's got to appear for both of them. There's only one that has both ticks, and that is red. So this probability of getting red and at least one red is going to be just the probability of getting red. Okay, if you're both at least one red and red at the same time, convince yourself that the only way that you can do that is by being red. Okay, that particular simplification that occurs frequently whenever you've got a numerator here, you've got an and at least one appears. You can use this simplification, and it helps you a lot, particularly when we do the harder questions in the Cambridge exercise. That simplification is very, very useful. So therefore, it's just the answer for B divided by the answer for C. So it's going to be 1/6 all over 5/6. And some people don't like compound fractions, so what they'll do is they'll do 1/6 and then they'll write the divide there, 5/6. And you can work that out to be 1/5, 1 out of 5. So that's the answer for part D. All right, we're going to do one more question. Okay, so we got a manager of a team notices that his team has a 2/3 probability of winning the game if it is raining. So let's think about how we can write that. Probability that we win given it's raining is 2/3. So the probability of us winning given that it is raining is 2/3. And a probability of 1/5 of winning if it is dry, given that it is dry. So our probability of winning given that it is dry is 1/5. The probability that it will rain on any day is a quarter. So the probability of rain is a quarter. First question says, find the probability that they will not win. Okay, so basically we're after the probability of not winning. Let's see if we can use the information that's given in the question to kind of draw a tree diagram. The first thing that I can sort of start off with is I can start off with the one that's not conditional at the beginning. So this would be rain. And where I think the assumption in this question is that because it says raining and dry, we're assuming that dry is the complement of raining. So if there's a quarter chance of rain, there'll be a 3/4 chance that it will be dry. And then you'll find out that these conditional probabilities we can put in the second column of our tree diagram. So let's have a think. We can either, if it's raining, we can either win or not win. If it's dry, we can either win or not win. Okay. I'm using not win rather than lose because I don't know if there's an option for drawing in whatever particular game they're playing. I'm not sure. So I'm just using win and not win. So let's think. So probability of winning, given that it rained, is 2/3. Okay, convince yourself that that is going to be this particular branch here. Winning, so W, given that it's rained. So it's rained, and what are the odds of us winning? 2/3 if it rains, which means that below it, that has to be 1/3, doesn't it? Because this particular branch here has to sum to 1. Likewise, let's see if we can work out what this one is. Probability of winning given that it was dry. So given that it was dry, we got a 1/5 chance of winning, which means 4/5 chance of not winning. Okay. So let me write the outcomes here. Rain, win, rain, not win, dry, win, dry, not win. Okay, we want to work out the probability of not winning. So there's 2 ways to not win. You can either rain and not win, or it'd be dry and not win. So I'm going to add those 2 probabilities, and that'll be the answer. Okay, so the first one, there's a 1/4 chance of it raining, and a 1/3 chance of us not winning there, and there's a 3/4 chance of it being dry times, and then dry and giving that they don't win when it's dry is 4/5. Okay, put that into your calculator. You should get 41 out of 60. Okay, that's part A done. Part B. Given that the team has won, so given that they've won, calculate the probability that it rained. So they're asking for the probability that it rained given that they've won. Okay, that's what we're after. Okay, so what we need here, probably the easiest way to do this is to use the definition. So using the definition or the formula, that's the probability of the intersection of raining and winning over the probability of winning, the back one down the bottom. Okay, now we know the probability of not winning is 41 out of 60. So probability of winning will therefore be 1 minus. So the probability of winning is 19 out of 60. Okay, let's have a think about the numerator here. Probability of it raining and winning. So probability of raining and winning, convince yourself that that's just going to be this top one, rain, win. Raining and winning. So therefore the numerator is going to be 1/4 times 2/3 over the probability of winning, which is 19 out of 60. Okay, put all that into your calculator and you'll get 10 out of 19. So that's the probability of it raining given that they've won. 10 out of 19. Just one thing that I want to highlight is that if you look at this last question here with the numerator and look at the tree diagram and do a bit of connecting, you'll notice the following. So I'll do it over here. You've got rain, you've got wind, and on the first branch that would be the probability of it raining. The second branch will be probability of winning given that it's rained. And the end here, the rain wind, that's the probability of the intersection of rain and wind. So that's the probability of rain and wind. And remember that when you go across a tree branch, you times. Okay, so this gives us an equation that the probability that it rains times the probability that you win given that it rained is equal to probability of it raining and winning. And then when you rearrange this, you can quickly see the conditional probability formula coming out. So that's the formula that we've been using for conditional probability. But you can see it as simply going across a tree diagram here and timesing. So it's a version of the product rule for conditional events or dependent events. Okay, what I'd like you to do is start exercise 707. Stop when you get to question 18. Oh, you should have already started it, but stop when you get to 18 because there's a bit more theory to do, and we'll do that in the next video. See you in the next video.